Sometimes it is not possible to differentiate an equation directly because it's not a function, but by using a technique called implicit differentiation, we can find the derivative. Hi, my name is Jason Rosenberry, and in today's lesson we will step into the mathematical realm of implicit differentiation. An implicitly defined function of x is one in which y is not explicitly or cannot be explicitly solved for x. To find the slope of a function like this, we use implicit differentiation. Let's look at a description of this. Implicit differentiation. To use implicit differentiation to find dy dx, we treat y as a differentiable function of x and differentiate both sides of the equation with respect to x using differentiation rules for sums, products, quotients, and the chain rule. Then solve for dy dx in terms of x and y together. Let's try some examples. Find dy dx for x squared y plus xy squared equals 6. So we will begin by differentiating both sides of this equation with respect to x. In other words, we will dy dx, the left-hand side, x squared y plus xy squared, and we will also differentiate with respect to x the other side of the equation, or just 6. On the left-hand side we have two terms, and each term is a product. So we will have to use the product rule for each one of those. So here we go. Let's differentiate x squared y with respect to x. Using the product rule, it would say first function, x squared, times the derivative of the second function, the derivative of y with respect to x, is simply dy dx, plus second function, y, times the derivative of the first function, derivative of x squared, is 2x. Now we'll do the next term. Again, we've got to use the product rule, plus the derivative of xy squared with respect to x. So again, first function, x, times the derivative of y squared with respect to x would be 2y to the first power times the derivative of y, which is dy dx. So there was an example of using the chain rule within implicit differentiation. Plus second function, y squared, times the derivative of the first function, x, which is just 1. Then over on the right hand side, the derivative of a constant, 6, is just 0. Now we want to solve this equation for dy dx. So here we see we have two terms that contain dy dx. So we want to get those two terms on one side of the equation, everything else on the other. So we currently have x squared times dy dx plus the other term that contains dy dx. So I'm going to write that term as 2xy dy dx. And now we'll take the other terms to the other side of the equation. So we will have a 2xy here to the other side becomes a negative 2xy. And we have this positive y squared to the other side, which is a negative y squared. On the left-hand side of the equation, we can factor out dy dx. So factoring out dy dx, we are left with x squared plus 2xy equals the right-hand side of the equation, negative 2xy minus y squared. And now we divide both sides by this quantity. So dy dx equals negative 2xy minus y squared over x squared plus 2xy. This could also be written as negative 2xy plus y squared over 2xy plus x squared. Here's another. Find dy dx for x plus tangent xy equals 0. So let's begin by taking the derivative of both sides of this equation with respect to x. So we'll dy dx, both sides of the equation. Here on the left-hand side we have two terms, so we'll differentiate each of those terms with respect to x. So the derivative of x with respect to x is just a 1, plus derivative of tan xy with respect to x. The derivative of tangent is secant squared, so we have secant squared xy, but now chain rule says we must go inside and take derivative of what's inside the parentheses there, what we're taking the tangent of, and that's going to require the product rule. So here we go with times derivative of that product, so we'll have times first function x times the derivative of y with respect to x, so that's dy dx, plus the second function y times derivative of the first function, which is x with respect to x, so it's just multiplying by 1. And then over here on the right hand side, the derivative of 0 stays 0. What we need to do now is multiply the secant squared xy times each one of those. So that gives us 1 plus x secant squared xy dy dx plus y times secant squared xy, and that is equal to 0, and we only have one term containing dy dx, this term right here. So we'll keep that on the left hand side of the equation, and we'll take the 1 and the other term to the other side of the equation. So that gives us x times secant squared xy times dy dx is equal to negative y secant squared xy minus 1. And now all that's left is to divide both sides by this expression. So dy dx equals negative y secant squared xy minus 1 all over x secant squared xy. Now this expression could be simplified also to negative 1 over x cosine squared xy minus y over x. Let's try one in which we need the second derivative. Find dy dx, then find d squared y over dx squared for y squared equals x squared plus 2x. So let's begin by finding dy dx. Let's differentiate both sides of this equation with respect to x. So left hand side, y squared, we would get 2y times dy dx equals, right hand side, the derivative of x squared is just 2x plus the derivative of 2x is just 2. We now want to solve this equation for dy dx. Notice we can divide both sides of the equation by 2, giving us y times dy dx is equal to x plus 1. And now to find dy dx, let's divide both sides by y. So dy dx is equal to x plus 1 all over y. So there's our first derivative, dy dx. So we have dy dx is equal to x plus 1 over y. Now let's find d squared y over dx squared, or the second derivative, by using the quotient rule. So that would equal the denominator, y, times the derivative of the numerator, which would just be 1, minus the numerator, the quantity x plus 1, times the derivative of the denominator, and the derivative of y with respect to x would just be dy dx all over the denominator squared, or y squared. Now we'll make a substitution. We know that dy dx is equal to this expression, so we'll substitute that in for dy dx, giving us y minus the quantity x plus 1 times x plus 1 over y, all of that over y squared. Now let's multiply top and bottom by y. That's going to give us y squared minus, these y's would divide out, and we're left with x plus 1 times x plus 1, or x plus 1 squared, over y squared times y, or y cubed. We do have one other substitution that we could perform and simplify our final answer. If we take the expression that we got for the second derivative, notice the original problem tells us that y squared is the same thing as x squared plus 2x. Our second derivative contains a term y squared. So if we take x squared plus 2x, substitute that in for y squared, and simplify, we end up with a really complete simplified answer. The second derivative, d squared y over dx squared, is equal to negative 1 over y cubed. In the law that describes how light changes direction as it enters a lens, the important angles are those the light makes with the perpendicular line to the surface. This is called the normal line to the surface at the point of entry. So again, we have at point of entry on a curved surface, we have the red line, which we would call the tangent line, and recall that the line perpendicular to the tangent line we call the normal line. We can use implicit differentiation to find the tangents and normals to a surface. Let's try an example. Find the lines that are A, tangent, and B, normal, to the curve at the given point. We're given x squared, y squared equals 9, and we're looking at the point negative 1, 3. So we have x squared, y squared equals 9, and the point negative 1, 3. Let's start by finding dy dx. So we need to differentiate both sides with respect to x using implicit differentiation. We'll use the product rule here on the left hand side. So the product rule would say first function, x squared, times derivative of the second function, so that would be times 2y dy dx, plus the second function, y squared, times derivative of the first function, which would just be 2x, equals derivative of 9, 0. We want to solve this equation for dy dx. So it looks like, simplifying, we get x squared, let's write this as a 2x squared y dy dx, and we would have plus 2xy squared equals 0. So it looks like dy dx would equal negative 2xy squared over dividing both sides by 2x squared y over 2x squared y. And this would simplify to negative y over x. Now we can use dy dx to find the slope of the tangent line at the point negative 1, 3. So let's evaluate dy dx at the point negative 1, 3. So we'll substitute negative 1 in for x and 3 in for y. That would give us negative 3 over negative 1, which is positive 3. So the slope of the tangent line is 3. The normal line, which is perpendicular, that slope would be negative 1/3. Now we can find the equations of our lines. Let's start with finding the equation of the tangent line. So that would be y minus 3 equals slope 3 times x minus negative 1, which is just x plus 1. So we get y minus 3 is equal to 3x plus 3, and adding 3 to both sides we get y equals 3x plus 6. So there's the equation of the tangent line at the point negative 1, 3. Using a slope of negative 1/3, we can find the equation of the normal line. So y minus 3 equals slope negative 1/3 times x plus 1 gives us y minus 3 equals negative 1/3 x minus 1/3. And we'll now add 3 to both sides. We get y equals negative 1/3 x. Adding 3, or adding 9/3 to both sides, gives us a positive 8/3. So the equation of the normal line would be y equals negative 1/3 x plus 8/3. Let's now look at a rule for taking derivatives of rational powers of x. Power rule for rational powers of x. If n is any rational number, then the derivative with respect to x of x to the n is n times x to the n minus 1. If n is less than 1, then the derivative does not exist at x equals 0. Let's differentiate some rational powers of x. For the following, let's find dy dx. Number 1, we have y equals the square root of x, which we know is the same thing as x to the 1/2 power. So therefore, y prime would equal 1/2 x, and now we subtract 1 off of 1/2, giving us negative 1/2. We can rewrite this answer as 1 over 2 times root x. Our second problem, we have y equals x to the 2/3 power. So y prime would equal 2/3 times x to the 2/3 minus 1. 2/3 minus 3/3 would be negative 1/3. And then rewriting this in radical form, we could write our final answer as 2 over 3 times the cube root of x. Now it's time for you to try a problem. Find dy dx given that y is equal to the quantity 2x plus 5 to the negative 1/2 power. Please pause the video while you work on this problem. When you are finished, restart the video to check your solution. So here we have y equals the quantity 2x plus 5 to the negative 1/2. So let's find y prime. So using our power rule, having rational exponents, this would equal negative 1/2 times the quantity 2x plus 5. We take negative 1/2 minus 1. Negative 1/2 minus 2/2 is negative 3/2. But now we got to also use the chain rule and take the derivative of the quantity. So the derivative of 2x plus 5 is 2. Simplifying, we have y prime equals, next we will take negative 1/2 times positive 2, gives us a negative 1. So negative times the quantity 2x plus 5 to the negative 3/2 power. In this lesson, we learned implicit differentiation and the rational power rule. Be sure to work the exercises that your teacher assigns. We'll see you next time.